All right. In this video, I want to describe different formulations, different equivalent formulations you can make for natural numbers. So um, you might have felt weird about describing natural numbers as something that contains one, and any natural number has a successor. So that's one way to describe what natural number is. But there are other equivalent ways that you could use. In certain contexts, it's a lot more convenient to do that. So I'd like to describe a couple of the other ways. Let's get started. Okay. So one equivalent way to describe induction is what's called strong induction. So how it's phrased, it sounds way more powerful than induction because the assumption you're making is a lot stronger, but it turns out that it's equivalent. Let's see what this formulation is. Okay, so here's strong induction. All right, let P of n be a sequence of mathematical statements. If the A and B below hold, then for every n in the natural numbers, P of n is true. So it has part A and part B as well, and they're very similar to how regular principle of induction is set up. But the second part, the B, is phrased differently. So part A is the same. P1 is true. So the base step is exactly the same. But how you phrase the part B is different. So with regular induction, we talk about if P of K is true, then P of K plus 1 is also true. Okay. So for K greater than 1, sorry, there's one extra 4 here. For K greater than 1, if P of I is true for all I less than K, then P of K is true. So you wanna show the assumption you make is P of I is true for every I less than K, then the step K is true. So instead of going from one step to the successor, you assume everything below it is automatically true. And then under that circumstance, you can show that the next step. So going from I strictly less than K, so everything up to K minus 1 is true, then you can also show that P of K is true. So that's how strong induction is phrased. And sometimes this is more useful because instead of going from one step to the next with a formula that's given to us, for example, sometimes you have a problem and you can break down the problem into smaller pieces. But maybe you can't control how big these smaller pieces are. So maybe you can break it up, the problem K into problem of size K minus 1. If you could do that, then just use the regular induction. But if you can't, if you break it up into several different pieces, but you can't control how small they are, this will come into play. Let's prove that this is this could be proved using regular induction. So I'm going to prove that the strong induction works by using the principle of induction. So that's what we'll do. So we will prove strong induction using principle of induction, the regular type. So what we do is instead of working with the expression P of n, we're going to make a new statement, Q of n. So Q of n is a statement that P of I is true for I from 1 through n. And then we'll apply the induction on this statement, Q of n. So the base step, by A, Q of 1 is true because Q of 1 is saying P of 1 is true. Induction step. So for the induction hypothesis, if we know that Q of K minus 1 holds, so that's the same as saying P of I is true for every I less than K, or I less than or equal to K minus 1. Then the part B says that if it's true for all I less than K, then P of K is true. So if we have that P of I is true for all I less than K, then we get P of K is true. But we already have Q of K minus 1. And then if we also include P of K, that means we have that Q of N is true. So every statement, I'm sorry, this index is screwed up. So this should be Q of K minus 1. Then we have Q of K is true. I will fix that in the notes. Okay. By the principle of induction, if we assume that Q of N minus 1 was true, and then we show that Q of N is true, so we went one step further. Never mind the fact that it doesn't really matter too much if we go from Q of K to Q of K plus 1, or Q of K minus 1 to Q of K. The way that's phrased, it's up to you, whichever phrase that makes more sense. But with the principle of induction, Q of N is true for all N. And that's the same as saying P of N is true for all N as well. Okay. I hope this made sense. Okay, let's do an example of a problem where strong induction will come into play. It comes into play because this problem is a problem of factoring numbers. So when you factor numbers, you get smaller numbers that are multiplied to get the same number. You can't control how this factoring works. So sometimes it's a prime number where you can't factor at all. But if it's a composite, if it's not a prime number, it's a product of other smaller numbers, but you can't control how much smaller it is. You can't guarantee that it's one less than before, right? For example. So natural tool to use here is the strong induction. So let's look at the statement. For every integer n greater than 1, n is either prime or product of primes. Okay, so we will prove this using strong induction. So in this problem, the base case should be n equals to 2 because there's a restriction where you should start the integer that's greater than 1. So that means the smallest case is the step n equals to 2. And n equals to 2 happens to be a prime number. So the claim is that it's either prime or it's product of prime. So 2 is already a prime. So it checks out. Let's go to the induction step. Suppose you have every integer from 2 through k minus 1 is either prime number or product of prime numbers. So let's look at the number k. K is either itself a prime number, and if it's not a prime by definition, it's product of strictly smaller integers. I say strictly because you could write prime number p as 1 times p, right? That's not making it factoring, making it smaller. If it's not a prime, then you could get non-trivial factors, which means it's strictly smaller integers that multiplies into k. Okay, so let's call these factors I and j. I can't necessarily guarantee that these guys are primes, right? We just know that it's smaller numbers that are multiplied to get the k. But what we could do is we could use the strong induction hypothesis. We know that any number strictly less than k is either a prime number or product of prime numbers. So if I and j themselves are prime, then we're done. If they're not prime, then it could be written as product of prime numbers. So you can break it up further until you get to primes. So either way, k is going to be product of prime numbers. Okay, so what we did was we used the fact that you could break it down for any integer strictly less than k, and we showed that k itself could also be done that way. So by strong induction, every natural number n greater than 1 is a prime or product of primes. Okay. So this is a case where strong induction comes into play. Yeah, so you might imagine in a certain fields of mathematics, like number theory, where they do care about primes and so on, product of primes. This type of induction will come into play more because you can't. Prime numbers are somewhat mysterious and difficult to control. But one thing that you can control about factors is that they get smaller as you factor further and further. So at some point you get down to primes. That's the idea. Okay. Another equivalent, another property that's equivalent to the principle of induction is what's called the well-ordering property of natural numbers. Okay. You say something is well-ordered, it is when you have a non-empty subset, you can always find the smallest element. Okay, so every non-empty subset of natural number has a smallest element. Okay. Turns out that this is a very interesting property about natural numbers, and it's equivalent to the principle of induction. I think in some sense, this statement is so simple that one might consider this as a more elegant definition. But I think principle of induction is more versatile to prove things. So I think our book's choice of choosing those principle of induction as like the definition of natural number is a good choice. But let's get to the proof of why this is equivalent to induction. Okay, so what we'll do is we will prove the well-ordering property is that the property that any non-empty subset of natural number has the smallest element using strong induction. Okay, so let's say P of n is a statement that every subset of natural number containing n has a least element. So that's a weird way to phrase things. So any subset containing natural number n has a least element. So if you can show this for all n, this is equivalent to well-ordering property, because if you have a non-empty subset, so every non-empty subset S contains, if it's non-empty, contains some natural number. And if it contains a natural number, then P of n implies that that set has a smallest element. Okay. I hope the setup of P of n, our choice of P of n makes sense. Okay, it is an awkward way to state it, but it makes it possible for you to prove using strong induction. Let's do the base step. Okay, so since 1 is the smallest, least natural number, every set containing 1 has a least element. In particular, 1 itself is the smallest one. So P of 1 is true. Inductive step. Okay, so if P of I is true for all I less than k, so any number less than k, if you contain it, then you can find the smallest natural number. Okay, so let S be any subset containing the number k. Okay, if S has no element less than k, then k is automatically the smallest element, so we're done. If k is not the smallest one, you can find some natural number I that's less than k. But we already know that if you contain a number smaller than k, then it has a least element. So we just show that P of k is true, right? It's either already the smallest element, or you can find something else that's smaller. And once you contain that number, you can get to the smallest element. By strong induction, we get that well-ordering property holds. Okay. Notice how well-ordering property holds for natural numbers, but it does not hold for integers, because integers you can go small and smaller towards negative infinity. For example, if you have a non-empty subset of like all even integers, you cannot get to the smallest one, right? So there's a big difference about proving things about integers or proving things about natural numbers. Natural numbers are set up in such a way that you can start somewhere and you can cover it all by moving forward from there. And you can't always do that with integers. Okay, so that's well-ordering property. And you might wonder how this is useful, like finding the smallest element. Well, you can kind of combine this with the proof by contradiction and get what's called method of descent. So here's one way to prove that something never fails. It's a weird way to set it up, but when you want to construct your argument in a contradiction way, sometimes you could use this. So here's the idea. Let S be a set for which some set of statement does not work. So suppose this statement doesn't hold. If the set S is non-empty, then it's a subset of natural number. So by the well-ordering property, it has the smallest number k for which it does not work. If you can show that having something that doesn't work implies that there's a smaller element that doesn't work, then we have a contradiction, because k was supposed to be the smallest element for it not to work, but you show that it's also not the smallest, right? So that would be the contradiction that you can create using this method of descent. Here's an example of something that uses the method of descent. Okay, so the proposition. So every natural number n can be expressed in exactly one way as the product of odd number in a power of 2. Every n could be the product of an odd number and power of 2. Note that in this setting, I'm counting 2 to the 0, which is equal to 1, is also a power of 2. Okay, so you could talk about odd number as well. All right, so let's prove this using method of descent. I think the key part that I want to show is that exactly one way to be able to write this. So it's a unique way to write a natural number. Okay, so let's talk about the proof. So if the claim fails, then there's the least n that does not have this such expression, that you cannot write it as odd number times power of 2 in exactly one way. So if n is odd, then n is not divisible by 2. Right? That's what it means to be odd. So 1 times n is a way to write that expression. Right? N is odd, and 1 is a power of 2. 2 to the 0th power. And there's no other way to write it because you can't divide by 2, so there's no 2 that you could factor out here. And if I chose a different odd number here, then you'll get a different number. So you don't get n as the product. So that can be true, right? If n is even, then you can divide by 2. So n over 2 is another such natural number. But if you can write this in as powers of 2 times an odd number, each expression for n over 2 could provide a way to write another expression for n by adjusting the power 2 by just 1, and vice versa. Like if you have an expression in n, then you could subtract 1 to get n over 2, expression for n over 2. So if n doesn't have a unique way to be written this way, then n over 2 doesn't have a unique way to be written this way as well. So if it fails for n, it also has to fail for n over 2. So we got a smaller counterexample. So if n is a counterexample for the statement, then n over 2 is also a counterexample. And n over 2 is smaller than n. So then n must have been not the smallest number that fails this test. So basically, the only thing that we assumed was that it fails for some number, right? If it fails for some number, then it has the smallest element. So it must be the case that no natural number fails this proposition condition. And that's the proof. So I hope that made sense. It is a little bit convoluted to work in this way, but sometimes that's the most natural way to prove things. All right, that's the end for this chapter. I will see you guys next week.